This is the data and AI platforms track, and let's begin this day with Petar Zecevic, Senior Principal Consultant at Poslovna Inteligencija. He will show us how Databricks in their products Apache Spark caused this seismic shift in the data analysis community. And please welcome to the stage Mr. Zecevic.
Okay, thank you. Thanks for coming. So I'm Petar Zecevic. I recently joined Poslovna. Poslovna means business in Zagreb, Croatia. I recently joined 3 months ago. And I'll show you an overview of the Databricks platform. The idea is to show you, the busy people, in a short presentation, the main things you can expect from the platform, how to use it, and what it offers. So Poslovna is 20 years old. We have offices in UK, Sweden, Austria, Slovenia, Croatia, more than 200 employees, more than 250 projects. And we do everything data, anything you can imagine with data. So about the subject, the Databricks Lakehouse platform. The team who built the Apache Spark started the company back in 2013. And they also started several other open source projects, Delta Lake and MLFlow, besides Apache Spark. And they also invented this data lakehouse concept. They are named a leader by Gartner in both database management systems and data science and machine learning platforms. They have more than 7,000 customers, more than 3,000 employees, and more than 3 billion in funding, which is just huge, especially for this area where we're from. It's just mind-boggling. So this data lakehouse concept marries data warehouses and data lakes. I'm pretty certain that most of you are familiar with data lake warehouses. They're built for efficient business intelligence reporting. However, they have poor support for unstructured data, data science and streaming workloads. They use closed formats, so you cannot just easily get a file that was generated by data warehouse and transfer it somewhere else. They're expensive to scale. It's not easy to add new nodes to those systems. On the other hand, we have data lakes, which can store any kind of data. They use cheap storage, off-the-shelf hard disks, cheap hard disks. And they allow for exploratory data analysis and also streaming use cases very easily. However, they're really complex beasts. There are lots of moving parts. Anybody who's tried to set up a data lake knows what I'm talking about. They offer often poor BI performance. They're not really tuned for things like that, and often devolve into people just start dumping data in data lakes and without much governance and oversight. Gartner tells us that 85% of big data science projects fail, but in 2022, almost $4 trillion of business value was created by AI, presumably by those 15% of projects that didn't fail. So why do data science projects fail? We have a recent MIT technology review survey of 600 C-level employees who said that 72% of them said that if their AI project would to fail, data issues are more likely to be the reason. And the processing speeds, governance, quality of data, and data sufficiency for models are the most important things they need to work on. The usual problems when building data lakes and those types of projects is that I've seen this a couple of times, that you have people start playing around with new technologies, and they expect use cases to pop up at some point, and then we'll figure out what to do with this shiny new toy. Sometimes that works, sometimes its use cases are well prepared in advance. However, this does happen. And often you get a data lake besides your traditional and main reporting database data warehouses in separate silos, and then you have to copy the data from one to the other often, or you need to difficult data from one. You need to access data from one to the other through some sometimes difficult interfaces. And you have two different systems with two different types of security mechanisms, and so it's difficult to apply the same security model to both systems, and difficult to apply governance at the same time to both. So that's where Lakehouse platform comes in. This is their pitch, actually. It unifies data warehouses and AI use cases on a single platform. It's built on open source and open standards, so you can just easily transfer your data to other systems, platforms. It's consistent across providers. They support Azure, AWS, and Google. It provides ACID transactions, atomic transactions, which it's still not really that common in this area in big data systems. They offer schema enforcement capabilities, which is something also we're used when working with relational databases, but still, surprisingly, it's not that common in big data world. And in one platform, they offer data warehousing, data engineering, data streaming, data science, machine learning, and data governance. So they integrate with all the major systems players in this area that you can think of. And this is what the GUI looks like once you log in. You have three personas that you can use: SQL persona, machine learning persona, and data science and engineering. Let me see if this works. Yeah. Okay. And SQL is not available unless you are using on Azure, for example, a premium account. But these two are available also with the free account. You can play around with those if you'd like, for free for trial period. So in SQL persona, we're working with queries, dashboards, alerts, and we're running our workloads on SQL warehouse clusters. We can also file upload data and look at data and so on, of course. In the data science and engineering persona, we're working with notebooks, so writing some code. You can access code from repos. You got your workflow, your workspace, where all of your uploaded files and the notebooks are accessible from. You can organize notebooks in jobs and pipelines, and you are running everything on clusters. And in machine learning persona, you also have all of these, plus experiments, models, feature store, and auto ML experiments. So there are two different main types of computing resources you can use. Clusters, it's just Spark components, drivers, and executors running in virtual machines. They are required for running anything in notebooks, jobs, pipelines. And then furthermore, you have all-purpose clusters and job clusters. These all-purpose clusters are more expensive than job clusters in DB units, Databricks units. And then you have SQL warehouses, formerly known as SQL endpoints. They're more optimized for BI workloads. And anything that you do in SQL workspace requires SQL warehouse, just to see the list of tables, to see the columns, and so on. Running queries, of course, and alerts, and etc. So you have two different cloud accounts. Databricks cloud account provides for the web application, for the GUI, for the repos, notebooks, job scheduling, and cluster management, and you have to have your own cloud account to pay for the clusters, SQL workspaces, and for accessing other data sources, and DBFS or Databricks file system. So I'd say the main technical foundations of the platform are Apache Spark. I hope everybody's here heard about Apache Spark. At least heard. Okay, half the room. I'm surprised. Jupyter notebooks. This is data science conference, so I again assume that most of you have at least seen them. You can organize jobs and pipelines in Jupyter notebooks. And there's Delta Lake, Delta Live tables, MLFlow for machine learning workloads and jobs, and Unity catalog, which is in preview. It's available, but in preview still, which offers audit log of everything that's done on the tables, and lineage. Then you can filter with SQL functions based on some access rights, and search also. You can search for, I don't know, columns or anything based on terms, and then you can access only those items that you have access rights for. So about Apache Spark, it's a general purpose distributed data processing engine. You can use it for any kind of workloads with data. It's running on many machines. Clusters, it's efficient and fast. At least it was the fastest big data processing pipeline when it appeared. Now there are, competition. There's competition. And it's got SQL. Subcomponents are SQL, streaming, machine learning, also graph processing component, which is not that often used. You've got APIs in Java, Scala, Python, and R. And it's really everywhere today. All of the major companies and small companies are using Apache Spark for various workloads, and it's part of other tools and products, and it's really everywhere. So it's really the main foundation of the platform. It's everything that you run in Databricks platform. It's run on Apache Spark. And on top of Spark, Databricks provides their own proprietary Photon execution engine, which is vectorized execution engine that can speed things up on some workloads. Then you've got Jupyter notebooks, which are web-based, interactive, collaborative. You're using your browser to write and execute code. And Databricks supports Python, SQL, R, and Scala. And open source Jupyter notebooks can support much more languages. They can also serve as documentation. You can write text, markdown code, and then export that into HTML, PDF, sent to your colleague. In Databricks, you can collaborate inside the platform on those notebooks. And inside Databricks, you can execute them as jobs and organize them in pipelines, which you cannot easily do with open source notebooks. And also you attach them to clusters in Databricks. Otherwise, in open source, you just run them on a server. There's no way to choose the, cloud cluster. This went down for some reason. You have notebook arguments. There are widgets you can define which act as arguments for notebooks. So that's also not easy to do with open source notebooks. You have to think of some custom code for that. And Delta Lake, that's a data storage framework built on top of Parquet file format. Parquet is the distributed file format, so data in a Parquet file is actually situated on many nodes. And Delta Lake is just a add-on to let's say Parquet, maybe we can say it that way, because it maintains a transaction log, which is just a JSON file, also on a distributed file system. Transaction log, which any commit and anything that's done on the table, it's written in this transaction log file, so that when those Parquet files can be huge, so when you do an update or delete, you have to write a new version of the file. So if you have, terabytes, that can take a long time. So while that's being done, old clients are reading the transaction log or the old version of the Parquet file. So once that's finished, it's written into that commit is written to the transaction log, and the new clients start reading that new version. So that's how this atomic part of ACID is implemented in Delta Lake. It's open source, you can use it on your own, but it's integrated into Databricks. And that also allows for upserts. Upsert is just like a merge statement where you say, I want to insert a new row or update an existing row if it exists. And you can do deletes, which is also not that easy to do in normal big data systems. So it also enforces schema, which you can turn off, so it will fail if the schema doesn't match, but you can ignore that if you like. You can do time travel, you can go back in time and versions to previous versions of the data. If it's still there, that can be huge, so you don't want to keep lots of versions around. And it handles the metadata about the files also with Spark, so that can also grow to huge levels. So there's no limit there. And in this way, it unifies streaming and batch processing. Then you have Delta Live tables, which have nothing to do actually with the Delta Lake. Only the Delta keyword is the same. It's a framework for building data processing pipelines, and I'll show you screenshots. You define transformations by defining live table definitions, and then you create new tables from existing live tables, and then DLT will just create a DAG or directed acyclic graph from those definitions, analyze your code, and then manage orchestration of those executions of those tasks, cluster management for maintaining your definitions. You just declare by SQL, declare your what you want to have in your Delta tables, and then it just runs continuously or by triggering it periodically. The DLT, let's say, system framework will manage your data to be current at all times. You have monitoring. You can define expectations to have some data quality assurances, and error handling logs and so on. You can do CDC with Delta Live tables, which is change data capture. That's a way to implement your SCD2, for example, slowly changing dimensions with historical data by issuing a command such as this one, query, apply changes into a table from a table. So it will monitor this table, and any delete, insert, update from this table will end up into this table as a separate row. So that's called SCD, or historical data. Then you've got MLFlow for machine learning workflows. That's a framework for managing machine learning life cycles. Consists of MLFlow tracking, which can track experiments when you, use scikit-learn, you build a model, it will automatically track all the parameters and metrics and runs that you did, and it will log them so you can go back to see what you used for each successful model, let's say. Then we have storage format for models, so that all the models of different flavors, scikit-learn, Keras, XGBoost, can be stored as in the same way. And also MLFlow projects, which packages all of the code related to a single machine learning projects together. So this is also open source stuff, so you can use it on its own, but it's also integrated in the platform. And you've got model registry, when you can register a certain version of the model in the registry and use that one as the current version of the model. So the whole architecture in one slide, that could be this. You have your batch data, streaming data coming into in various ways into the platform. They promote this multi-hop architecture, as they call it, separating the layers of the data into bronze, silver, and gold. Bronze is just raw data, kept as it is when it enters. Then silver is augmented, filtered, cleaned data, and then gold, which contains some aggregations. This can all be streaming, except for the last one. Aggregation will break the requirements for streaming sources. So if you have some aggregated data that cannot be handled as a streaming source further down the line. You've got machine learning stuff, you've got data warehousing stuff, and it all sits on the platform itself and the cloud environments, and then you have lots of integrations and with different clients. So I'm going to show you, previously I showed a live demo, but there's no time for this, so I'll just show you a bunch of screenshots. I hope it will do. So this is a data explorer, which is available in SQL Persona. It offers what you would expect from a, let's say, relational database client. You can list your databases and tables. You can see the schema of the table. This one is a delta table, which is the default in the environment. So you have history of the table. You can define permissions and sample data. See the sample data. It's all running on this SQL warehouse computing environment. So we could not list the tables or see the schema without this. So you can grant permissions as you would expect. Then you've got SQL editor. Also familiar, for example, if you've used Beaver or anything similar, but with some different additions. First of all, you can inspect the runtime here by clicking on this link here that shows how long the query took. If you click on that, you can see some details from Spark, because it was all planned by Spark, Spark Planner, and executed by Spark. So you can look at the query profile and how long each step took. So the Spark Planner will split the query into different stages, and you can inspect each stage to see, if you have data exchange among nodes. That's the usual culprit. You want to minimize the, how much data is exchanged. And also you can see how much data memory each step took, how long it took, how many rows each processed, and so on, and lots of other things. This is also available through the web UI from Spark, but this is much more nicer and user-friendly here. And you can also do, by clicking on this plus here, you can create a visualization. This one is just simple bar visualization. You do all kinds of visualizations. And these two things here are those widgets I mentioned before. This one is a filter widget, filtering on a date column, and you can choose to filter on per day, per month, per year. If you change a value, this graph will change automatically. And this one is a parameter widget, which has a type. This one is integer, and a name of the parameter, which can be used then in the query. So if I change this here and click apply change, this will change based on this query, right? So you can use all of these visualizations created here are registered in the environment, so you can reuse them inside the dashboards. And also all of these widgets are automatically added to the dashboard, so end users can use them, filter the data, and so on. This is just New York Taxi trip analysis sample dashboard. Then we've got Jupyter Notebooks, which is really another core part of the platform. Because most of the programming and stuff is done through them. So they consist of cells. This cell is a markdown cell. You can write some documentation here on introduction or whatever. You've got code, cells, and you can execute each one separately. You can change the default language here. This is not available, easily done with open source notebooks. So Python is the default language. If I execute some SQL code, it will complain. So I can execute Python by default. It needs to run on a cluster, chosen here. So here I'm using the display built-in function by Databricks, which will format nicely any result, and also the utility package from Databricks that will, for example, list files in a folder. So you can schedule a notebook to run at a certain time to send an alert if it fails, starts, succeeds. What else? You can set permissions on notebooks. Read and write and so on. And plus, you can inspect each command. All of it runs on Spark cluster. You have Spark variable here predefined, and so you can inspect every job that's triggered by Spark job that's triggered by your query. And this is all available from the Spark Web UI, but here it's much more user-friendly. For example, for streaming queries, you can see right away how much data it's using and so on. Then you can organize notebooks in jobs. So you choose your notebook, add a task, and then that will be part of your job. You can add some parameters, choose the cluster where it's run. And then you can also use Delta Live tables, which are also special jobs, let's say. So you built your Delta Live table notebook. You define your live tables. Note the live keyword here. So if you try to execute this cell, it will say that the Delta Live table query is syntactically valid, but you must create a pipeline in order to define and populate your table. So this does nothing on its own, only when it's part of your pipeline. So to create a pipeline, you click Create Pipeline. And then you choose your notebook. You can add some configuration parameters. You can choose the continuous mode, execution mode, or a triggered. Continuous means that it will just keep processing data in the background and keep your data fresh. You can choose the cluster size, and it will give you an estimate of the cost in dB units here per hour. So once you start your Delta Live table pipeline, it will create some resources, set up tables, and then it will give you this nice graph that you can, this is the DAG, directed acyclic graph, that it created out of your definitions from the notebook. And it shows you live how it's running. You can click on each and see some details. You can inspect, you can open up the Spark UI, you can inspect logs and metrics and so on. So there's no time to go into other stuff, but it's a really complete platform. You have your command line interface and REST API with which you can do mostly everything on the platform. You've got AutoML, which will you point it to a table, to your data, and choose a type of machine learning thing that you want to do. I guess you're familiar with those things. As for example, classification, regression, it will automatically generate a notebook with complete code that you can run to analyze the data. So it's not really, completely user-friendly, next, and the graphical. You get code as an output. And there's also feature store, which is just like special kind of table that's used inside and reused inside your machine learning workflows. You have streaming stateful operations. You can do stream joins, stream static joins. You can clone tables, create a table, deep cloning the other table. You can use autoloader to continuously ingest files from cloud resources or from local folders. You can send, you've seen already alerts, and you can send emails and so on. And there's no time to go into machine learning stuff, but I hope you get the idea of the platform. If we have time for questions, I'm here or later.
So we'll have a short question round.
Can you say, please, do you have some support of this stuff in main IDE? So maybe notebooks will be available in some IDEs.
Sorry, I didn't hear you.
Huh?
Can you repeat, please?
Do you have support of notebooks in some main IDE like IDEA, VS Code, and others?
So if you can write your notebooks inside,
Yeah.
well, you can sync your. You can use a repo, so you can author, write your notebooks in an idea and.
I can open the node from repo. I know that it has some special format of notebook. It's not just Py or Scala file. Yes.
It just uses a what do you call it? Comments inside the notebooks. Comments with special commands. So it can understand your notebooks that you would write in IDEA or whatever, but some of those things would not be available then. You would need to, yeah. Or you can write your notebook, your Python code, whatever, in some library, then push that to repo, and then use that, something like that, maybe.
But I want to edit notebook in IDEA because it's.
Yeah, I'm not sure if that's possible out of the box. Yeah.
We'll have time for one more question, and then we have to move on.
Thank you for your presentation, Mirna Škobel, Robert Bosch. We are heavily dealing with the Databricks platform, and my question goes towards SQL endpoints. So what is your experience in poslovna inteligencija? I'm not asking about the benchmarks regarding SQL endpoints. What are advantages and the disadvantages? I'm asking about cost and performances.
Well, they're, first of all, more expensive. You have to have a premium account and so on, and they should be optimized for BI workloads. I think you can gain the same performance with Photon execution engine with data engineering stuff. This is just more user friendly. You can do the SQL editor. That part of the functionality is not available without the SQL warehouse. So you're just limited with the amount of you're forced to use it, right? There's no. No, that's the main argument, I guess. You can do all of that stuff from the clusters from Spark code. You can do the same thing. It's not that user friendly. So the idea is to have users that are making dashboards and all that kind of thing. They would use warehouses.
That would be all. Thank you, Petar.